So we'll start with the lecture, yeah? Okay, so today's topic, we'll continue with the lecture Friday, drug metabolism. Okay, so mentioned earlier, last week, drug metabolism is also referred as drug biotransformation, the change in the chemical structure of an absorbed xenobiotic within a living organism, and usually by enzyme catalyzed reactions. So a parent drug or parent compound will be converted to metabolite in order to be eliminated by the body. So many lipid-soluble weak organic acids or bases, they must be metabolized to more water-soluble metabolites. Okay, so they need to be in the water-soluble form. Polar compounds. So polar compounds is referring to water-soluble compounds. They are readily excreted in urine and bile. Okay, so the excretion is in urine and bile, but they must be in uh, the polar compound or with high lipid, with high water solubility. So metabolism often results in inactivation of the compound. Some drugs are activated by metabolism, such as corticosteroids. So corticosteroids are referred as prodrugs because they are activated upon metabolism. Example, prednisone. This is a drug, prednisone, is converted by liver enzymes to prednisolone, which has the anti-inflammatory property or activity. So prednisone, it's being converted by the liver enzymes after metabolism and produces the metabolite, which is prednisolone, which is an active compound which has the anti-inflammatory property. So where are drugs metabolized? So the main organ is the liver, and other organs are lungs, gastrointestinal tract, skin, and kidneys. Biotransformation reactions are catalyzed by cellular enzymes that are located in the endoplasmic reticulum, cytoplasm, mitochondria, cell membrane, and lysosomes. So today I will discuss the hepatic enzymic metabolism because that is the main organ that metabolize drugs. So I won't discuss the others. So this is the main organ that's involved in metabolizing drugs. Okay, so hepatic enzymic metabolism. There are two phases. Okay, phase one is referred as functionalization. Okay, so what is functionalization? It's actually the addition of a functional group, the OH group, by the process of oxidation, reduction, or hydrolysis. Okay. So what is oxidation? Oxidation, is the addition of oxygen or removal of hydrogen ion. Reduction process would be the addition of hydrogen ion to the drug molecule. Hydrolysis Yeah, this happens, with chemicals with either the ester or amide linkages. Okay, so hydrolysis happens with compounds with ester or amide linkages. So functionalization occurs here. Yeah, so that's where the drug will be converted to metabolite. So in the first phase, yeah, there will be increased water solubility of the drug, and it can be inactive or uh, less active or more active. Okay, so inactive, less active, or more active. So if the metabolite is more active, the drug is referred as, anyone? If the drug is more active after phase 1 metabolism, what do we call the drug?
Metabolite.
It's a metabolite, yeah. But what is the terminology that we use for drugs that undergo first 1 phase, they become active? Pro-drug. Remember I explained just now, yeah? The
Yes,
previous
sir.
pro-drugs, right? They are referred as pro-drugs. Okay, drugs that are converted to metabolite, yeah. So that drug, corticosteroid, is a pro-drug, yeah, which is upon phase 1 metabolism, they become active metabolites. Okay, the metabolite, yeah, the prednisolone, yeah, that is the active metabolite, yeah, has got the effect or has got the anti-inflammatory property. It's active, you know, so the metabolite is active. Is that clear? Ken, do you understand? Hello?
Yes, doctor.
Yes,
Yeah.
okay. So active metabolites, yeah. So drugs converted to active metabolites are referred as prodrugs. So now phase 2, so from the metabolite, yeah, it will be converted to conjugate. Okay, what is how the process happen? Yeah, in phase 2, conjugation process occurs. Yeah, here the endogenous substances, yeah, combines with the functional group from phase 1. Okay, what are the endogenous substances? These are like glucuronic acid, yeah, sulfate, glutathione. Okay, basically glucuronic acid. Yeah, all these are from the uh, from the food that we eat. Yeah, that's why it's written there endogenous substance. Glucuronic, yeah, is derived from glucose. Okay, so uh, conjugation process, yeah, the endogenous substance, yeah, such as glucuronic acid, the sulfate, glutathione, they will combine with the functional group from phase 1. Okay, because here you will have the functional group OH and so on, and then it will combine with the glucuronic acid and the compound, the end product, yeah, which is a conjugate, yeah, is highly water soluble. You see the 3 arrows, yeah, this is only 1 arrow, this is 3, yeah? 3 times increase in water solubility, yeah, of the product, and here after undergoing second phase, yeah, usually, yeah, they will be inactive. Okay, reduce biologic activity. First phase, yeah, they can be inactive, less active, or more active. But after going through the second phase, definitely they are not active anymore. Yeah, the activity, they don't have any activity already. That means they are ready to be eliminated by the body. Okay. So the characteristic of phase 1 reactions, it makes the drug more reactive and capable of combining with polar conjugating groups. Okay, so these are the, it will, it makes the drug being able to combine with the conjugating groups such as the glutathione and so on. Okay, that's the first one. Then substrates are highly lipid soluble compounds. Okay, so the substrate that's been produced, it's lipid soluble. Yeah, that they are highly lipid soluble compounds. The metabolites are more water soluble. Okay, so the substrate is lipid, but the product that being produced after undergoing phase 1, they are more lipid soluble and aspirated or undergo phase 2 reaction. So what are the types of phase 1 reactions? Okay, mentioned just now, oxidation, oxidation, reduction, and hydrolysis. Okay, these are the three types of processes in phase 1. So oxidation, most common reaction, involves the addition of oxygen, removal of the hydrogen from the drug. So for example, the hydroxylation of pentobarbital, yeah, uh, with the enzyme group, or family of cytochrome P450. Okay, so this actually this is just a family. This is a group of enzymes. So beneath the cytochrome, there are many sub enzymes that are involved in the hydroxylation of pentobarbital. Okay. So reduction is the addition of hydrogen to the drug molecule. For example, like chloramphenicol undergoes reduction process, phase 1 metabolism. Hydrolysis, okay, are chemicals, with or drugs with either ester or amide linkages, So the enzyme would be esterases, yeah. So esterases are responsible, yeah, for the hydrolysis, process in acetylcholine, okay, for drug acetylcholine. So these reactions, they introduce functional groups. It could be OH, or NH2. So the characteristic of phase 2 reactions, okay, it couples, with phase 1 metabolite with substrates from the diet, okay, and produces the conjugate. So phase 1 metabolite will combine with sulfate, or glutathione to produce the conjugate, which is highly water soluble. Okay. So conjugates are polar. Polar means water soluble compounds. Okay. So conjugates are highly water soluble. They are inactive and readily excretable. It's ready to be excreted by the kidney. So conjugating substance, I mentioned earlier, I gave example, the chloronic acid, sulfate, glutathione, the methyl groups, glycine, cysteine, methionine, all these are the conjugating substance which will combine with the metabolite. So types of phase 2 reactions, there are many, I'm just going to show you a few here, a few examples. I think there are about 9, of phase 2 reactions. The rest you can refer to books. So here I'm just going to show you some examples. So the important one, glucuronic acid conjugation. So this one is via the enzyme glucuronyl transferase. Okay. So So glucuronate transferase is the enzyme, okay, that involved in the conjugation process. So this is a very important pathway, yeah, because most of the drugs undergo glucuronic acid conjugation. Yeah, example of drugs, yeah, listed here: morphine, acetaminophen, salicylic acid, chloramphenicol. So individuals, yeah, that are deficient in glucuronide synthesis, they will they'll be unable, or they'll be slow lah, yeah, in metabolizing the drugs. Okay, so individuals deficient in glucuronide synthesis, if they cannot produce, yeah, glucuronide, yeah, their body, yeah, uh, they will have problem, yeah, to metabolize many of the drugs. Sulfate conjugation. Okay, so sulfate, uh, the enzyme that is involved is sulfotransferase. Okay, mainly phenols, alcohols. Yeah, they are conjugated to sulfate. So drugs, yeah, that undergo sulfate conjugation are acetaminophen, morphine. Okay, so you can see here one drug, they may undergo one or two or many, yeah, phase 2 reactions. Okay, as you can see just now, yeah, acetaminophen, yeah, uh, it it involves in the glucuronic acid conjugation, and also it also undergo sulfate conjugation. It's not like one drug will undergo just one conjugation. No, it can undergo many types of type 2 metabolic process. Yeah, sulfate, and then if glucuronic acid conjugation process is saturated, they will undergo like sulfate conjugation, and then the body will try to eliminate the drug, by other means of conjugation, yeah, so that it's ready to be excreted by the body. The third one, yeah, is acetylation. Okay, so this one refers to N-acetyltransferase enzyme. Yeah, usually occurs with drug that has NH2 group. Yeah, so mostly sulfonamide. Yeah, sulfonamide is antibacterial drug. It's also used for coccidiosis. Sulfonamide. So so most, yeah, of these drugs, yeah, under the sulfonamide group will undergo acetylation. Okay, so uh, uh, dogs, yeah, dogs, especially dogs, they have reduced or low in N-acetyltransferase enzyme. So therefore, drugs like sulfonamide, yeah, it's not the choice of drug, yeah, to treat bacterial infections in dogs because of the deficiency in the metabolizing enzyme. Okay, another example would be glutathione conjugation. Yeah? So this involves the enzyme glutathione S transferase. So mainly for anti-cancer drugs. These are all that requires the glutathione conjugation process. So the rest, yeah, there are five more. Yeah, I think. If you want to know, like more examples of phase 2 biotransformation, hepatic biotransformation, yeah, please refer to the books. What I've cited here are just examples. Okay, so far, okay with phase 1, phase 2 metabolism, hepatic metabolism.
Yes.
Okay, so who answered my question? I know the name.
It's me, Dr. Hazikri.
Haziq, yeah, Haziq. So your yes is always long, yes. Dia macam mengaji, ya. Dia ada harakat, dua harakat, empat harakat gitu. Okay, right. So now we look at on factors, yeah, that affect drug metabolism. Okay. So number one, age. Yeah, age of the animal. Less than 1 month old animals are deficient in metabolizing enzyme. So older animals are less able to synthesize liver enzyme. Okay. Usually older animals, they have some problems and so on. And then their liver enzymes also has decreased. So they will have some problem, yeah, to synthesize liver enzyme. So in young animals, yeah, less than a month old, okay, they have less metabolizing enzyme. Therefore, in this category of uh, animals, yeah, you must be very careful, yeah, using drugs. Okay, so the dose, yeah, should be uh, should be reduced, yeah, for animals that are very young and also in geriatric patients. Okay, like us, normal, yeah, normal people, yeah, don't have any problem, don't have any liver disease or any systemic disease, then it's okay. The normal dose uh, will be no problem for us. Okay. Number two, distribution. So drugs, yeah, that are bound to plasma, yeah, or stored in fat, yeah, they are not available for metabolism. Okay. Therefore, when the it's not like they are not available at all, for metabolism. They are bound to plasma, but eventually, yeah, because as you know, binding of proteins to drugs, yeah, is not a permanent binding, yeah. So whenever a free drug moves from the systemic circulation, yeah, so the bound drug will be unbound. So they have to stay at equilibrium. Okay, so it is like uh, being released slowly. The what do you call, the bound drugs, yeah, will release the molecules slowly, yeah, as compared to the unbound drugs, yeah? Okay. And when they are stored in fat, eventually they'll be released slowly for metabolism and uh, excretion. Okay. Only thing, it takes longer time, than the normal process. Yeah. Number three, disease. Okay, liver pathology or dysfunction. Yeah, reduces the biotransformation ability of the liver. So if anyone suffering or animals having a liver problem, yeah, usually before we do their before we treat them, we will check the liver function, kidney function, and so on. So if it's all like within the normal range, it's no problem. But if you have like animals with liver disease, then the drugs that you administer, yeah, must really be careful with the dose. Need to adjust the dose accordingly, yeah, to the animal. Okay. Then the species differences. Cats have reduced, yeah, glucuronil transferase, right? So activity, and they metabolize drugs such as aspirin or paracetamol very slowly. Okay, so in cats we do not give aspirin or paracetamol. Why? Because of the reduced quantity of the glucuronil transferase enzyme. So this enzyme is very important to biotransform the, the drug, yeah, to be inactive form. So dogs, yeah, they have actually dogs and cats, both of the species, they have deficient in glucuronate transferase enzyme. But in human, no problem. So can a human being take? Can a human take paracetamol? Is it safe for a human to take paracetamol?
Yes.
Anyone?
Yes.
Can?
Yes.
Okay. Right. So in cats and dogs, yeah, uh, we do not, yeah, do not give paracetamol. The toxic dose is in cats especially. Cats are very susceptible. Yeah, uh, the dose as low as 50 milligram per kilogram. Yeah, is already the toxic dose to the animal. Okay, 50 milligram. Okay, genetics. Okay, on genetics, lack or mutation in the metabolizing enzyme variability, uh, they can affect the drug metabolism. So the metabolism, yeah, uh, the enzyme variability, it's either they are deficient, yeah, or they are fast or slow, okay, producing, yeah, can affect the drug metabolism. So, for example, in the colies, yeah, so colies are sensitive, yeah, to ivermectin. So this is because of the mutation of the MDR1 gene. Okay? So the MDR1 gene has been mutated, so therefore, they are prone to toxicity at the normal dose of ivermectin. So in colies, uh, you can, yeah, but you must be very careful when you administer ivermectin. Okay, so far with drug metabolism, any questions on drug metabolism? All are good. Can I proceed?
Yes, doctor.
Yes. Okay, we move on to drug elimination. So this will be the last phase after the drug is being administered, being absorbed, distributed to the target organs, and then giving the effect, and then it undergoes metabolism, and lastly, it has to be eliminated from the body. Okay, what is drug elimination? It's a drug or a metabolite, yeah, that is eliminated from the body. Okay, so what are the organs involved? Kidney. Here, kidney is the main organ. Kidney, followed by liver, lungs, yeah, lungs for volatile drugs, intestinal tract, yeah. So and then the other organs, yeah, be through elimination would be through tears, yeah, in milk, eliminated in milk, and also through sweat. So rate of elimination. So the rate of elimination determines uh, the duration of action. Because if the rate of elimination is very fast, yeah, so the drug will be out from the body very fast. So the duration will be short. Most drugs, yeah, eliminated, yeah, the elimination process, from blood follows exponential first order kinetics. So most drugs, they're eliminated through first order kinetics. So what is first order kinetics? Is actually the rate of elimination is proportionate to drug concentration. Okay, let's see the graph here. So this graph shows the first order elimination. Okay, so you can see here, yeah, the y-axis drug concentration, yeah, is in percentage versus time. Okay, so it shows here, yeah, high concentration. When the drug is at high concentration, the elimination rate is also high. It's fast. You see the drop, yeah? So it's coming down very fast. Okay. When the concentration is low, the, the rate of elimination will be slow. So this is first order elimination kinetics. Drugs, yeah, eliminated by first order kinetics, the fractional time. So just now I showed you the graph, the plasma, yeah, the concentration in plasma versus time, yeah, plasma versus time will be equals to the elimination half-life. Okay. So if the drug is eliminated by first order kinetics, yeah, the fractional change in drug plasma and time, yeah, is referred as elimination half-life. So what is elimination half-life? This is a time taken, yeah, for the plasma concentration of the drug to decline by 50% due to excretion. So it has dropped to 50%. So when the drug plasma drops to 50% due to excretion, so that would be the time taken, yeah, to drop to 50% would be the elimination half-life of the drug. Elimination, yeah, can be saturated after high doses of drugs, yeah, that follow zero order kinetics. So when the elimination process is saturated, yeah, after high doses, then it will follow, yeah, zero order kinetics. Yeah, for example, the rate of elimination is fixed, yeah, and independent of plasma drug concentration. No matter how high the plasma concentration, the rate of elimination is fixed. Okay? Whereas the other one, yeah, the first order kinetics, high concentration, high rate of elimination. Yeah, but in zero order, yeah, whether it's high or low, it doesn't matter. The rate of elimination is fixed. Yeah, it will be fixed at a rate. So this graph, yeah, shows zero order elimination. Okay, so elimination is constant regardless of concentration. So you can see again, the y-axis is the concentration of drug, x-axis is the time. Yeah. So here, okay, concentration, let's say at from 100 to 80, yeah, 80%, it is being eliminated. Yeah, the rate is it's 2 hours. Yeah, 2 hours. It takes to
Doctor, we can't hear you. Hello, doctor.
Hello, doctor. Doctor, sorry, we can't hear you.
Can you hear me now?
Yes, doctor, I can hear you.
Okay. Can you put down the phone?
Okay.
Okay, I go back. Okay, sorry for the problem. I think my headphone. Maybe something went wrong there. Okay, so this part. Okay, so starting from this part, you couldn't hear me. Now it's okay.
Doctor, I can hear you since the last slide. The graph.
Which last slide?
The graph, the zero order graph.
This zero order.
Yeah.
Okay, this slide is okay.
That one is okay.
Okay, so I repeat the slide.
Okay, thank you, doctor.
So this is zero order elimination. Yeah. So elimination is constant regardless of concentration. So if you look at the graph, drug concentration percentage. Yeah. So when it drops from 100 to 80%, drug concentration, it takes about 2 hours. To drop from 100 to 80. If I draw a line here, you can see. So from 80 to 60, it is when I draw a line to the graph graph line, this line, I will see that it is at 4 hours. That means from 80 to 60, it has taken another 2 hours. The concentration to drop 20%. So 60 to 40, another 20% drop in concentration. If I draw a line, it is at the sixth hour. Okay, which is another 2 hours. So the concentration is dropping every 20%, from 100 to 80, 60 and so on, at a constant rate of elimination, which is 2 hours. So every 2 hours, there is a drop in the concentration of the drug. So the elimination is constant. So every 20%, it's dropping. Every 20% drop of the concentration, it takes 2 hours, for the drop in the concentration. So that means the elimination, is constant. 2 hours, 2 hours, 2 hours, regardless the concentration, whether it's high or low, it's the same. Okay, so the difference between the first order elimination, I've mentioned that when the concentration is very high, the elimination rate also high. When it gets very low, the elimination rate is low. Whereas zero order, no matter high or low concentration, the elimination rate is constant. Is that okay?
Okay, doctor.
Can, Okay. So 3 clinically important drugs that follow zero order elimination kinetics are ethanol, phenytoin, aspirin. Okay, so phenytoin is used for epilepsy. Do you know epilepsy? So it is a drug to control convulsions or seizures in animals. Okay, so this is an anticonvulsant drug. Anticonvulsion. Are you familiar with the term convulsion? Okay, anticonvulsant is anti-convulsant. ANTI is anti, convulsant. CONVULSANT. It is a drug to control convulsions or seizures in animals. Okay, as you know, aspirin, yeah, aspirin can be used for as a painkiller. Okay, so aspirin is can be bought, yeah, over the counter, but be careful, yeah. So aspirin, you cannot take high doses of aspirin. It can lead to toxicity because the elimination is by zero order elimination. Okay, is that okay? Clear?
Uh,
Right.
Doctor,
Yes.
what do you mean by
Speak louder. I cannot hear you.
what doctor? What do you mean by toxicity? Like,
I cannot hear you. No,
hello,
Raihana, you
doctor.
have to speak louder because I'm not using the microphone. Huh?
Doctor, can you hear me?
I'm not using my headphone.
Doctor, can you hear me?
It's not clear.
Then
Oh, you write in the chat.
okay, okay.
Ah. Okay, I can't see anything in the chat yet. Any questions so far? I think I will show I will explain the diagram, yeah, on drug elimination tomorrow. So already you got a class at 10, right?
Yes, doctor.
Okay. So it's going to take a while, yeah, to explain the drug elimination process. So any questions? Raihana asked me something, but I couldn't hear her. You need to write in the chat box, or you need to speak like who is that? Nimi. Now who said yes, doctor? Nimi, yeah.
Me, doctor.
Yes, so I can hear Nimi very well, but I couldn't hear Raihana's question. Anyone?
Dr. Raihana has typed her question in the chat box.
I'm looking at the chat box already. Okay, she's typed. All right. Okay, she asked me, can you explain why zero order elimination? Okay. Can lead to toxicity. Because zero order elimination, as I explained, if you take like many pills of aspirin, right? The elimination is at a constant rate. So the drug is in the body, okay? It's not being eliminated at a normal rate, right? So when it's not being eliminated, you take high doses of the drug. Therefore, all drugs, yeah, they are not safe. Okay, they need to be eliminated by the body at certain time. So that's where we have like certain doses you take. Okay, morning you only can take one pill, and then the afternoon, two pills. Yeah, or else if like all the drugs, if they are safe, yeah, you can say okay, take whatever you want, isn't it? So, in order to avoid the side effect or the toxicity of a particular drug, so drugs are given at certain intervals to produce the effect. So, if you give like at one time, yeah, you take 20 tablets of aspirin, okay. Even like paracetamol, you only can take 8 tablets in a day. Okay, so like aspirin, if you take more than that, yeah, it will follow zero order elimination. It cannot be eliminated. It will take time to eliminate the 20 tablets. It can only go at certain interval, and that 20 tablets produces toxicity. It will cause damage to all the enzyme, yeah, it cannot be metabolized, cause damage to the kidney and other cells in the body. It cannot be eliminated. The drug is in the body system, yeah. Because it's no longer the normal rate of elimination, yeah. The normal rate, yeah, when you have like high concentration, so it will go accordingly. Okay, high concentration, the elimination process also will go at the same speed. Yeah, with kidney failure or liver failure or whatever, yeah. So the dose has to be lower because it doesn't go at the normal rate of elimination. It stays in the body. When it stays longer in the body, yeah, it's not being eliminated, then you see the side effects and the toxicity to the body cells. Yeah, they can produce toxic compounds, yeah, and injure blood vessels and red blood cells and other cells in the body. Yes, paracetamol also, yes, follows the zero order elimination. That's why they only restrict like 8 tablets in a day. Because you take more than 8 tablets, yeah, it will produce a toxic compound which cannot be eliminated by the body because of the zero order elimination. Okay. Is there any questions? Yeah. So with some drugs, they will say you don't exceed this amount in a day because the body cannot eliminate the drug. Yeah, because of the difference in the elimination process of the drug. So far, okay? All clear? Can I stop here for today? Any more questions? I hope I answered your question. Was it clear? Any response from the class? Can I stop the class? Can I stop the lecture? Was
Yes,
that clear?
doctor.
Was that clear?
It was clear, doctor.
Okay, right. So I will see you tomorrow then at 10 o'clock.
Thank you so much, doctor.
Okay then, see you all. Bye.